Hello, everybody. This is Miss Peachy from your WCA Physics A class, and I am doing a little lesson kind of overview for Unit 4, Lesson 6 on correlation and causation. Our keywords here are acceleration, causation, correlation, force, and mass. So let's kind of delve into the main point of the lesson, shall we? So when we're looking at the main points from this lesson, so this one's a bit tricky because it's really trying to teach you the difference between correlation and causation by using some of Newton's laws as an example. And I'm not sure it's like the best example to use. I actually like the example they give in the podcast a little bit better, but let's kind of go with what they have here because it's a very important concept to understand. So essentially, it's saying that let's look at some dominoes. If I do some experiments and I just leave the dominoes sitting there, that they're going to kind of remain in one place unless an outside force acts on them, has to push or pull the dominoes. If a net force acts on the first domino in the line, the dominoes will have an acceleration, which is a change in velocity. From Newton's second law, the net force on an object is the product of the mass or the amount of matter in the object and the acceleration of the object. Without net force, there's no acceleration. With increasing net force, you increase the acceleration. So it says that you are basically correlating force and acceleration here. One quantity does seem to change the other quantity as well. So correlation means that the two are related in some way, shape, or form, right? There's some relationship there. We can't determine if one actually causes that, but there's definitely a relationship. An example might be there is a correlation between being sedentary and increased risks of cancer, right? So we can say that there's definitely some relationship between not having enough exercise and an increase in the risk of cancer, but we can't directly say that you're going to get cancer if you don't exercise, right? It doesn't necessarily cause cancer, but there's definitely increases your risk. It's correlated in some way, shape, or form. When you kind of look at this specific thing kind of more closely, correlation can be positive, which means that as both quantities increase, as you increase one, the other one increases, or it can be negative, meaning as you increase one, the other one decreases, kind of have the opposite effect of each other. But if one actually causes a change in the other one directly, then we can say it's causation, meaning one event is the direct result of another. Um, for example, let's say, so um, you don't eat and your stomach growls. That's causation, right? Because one event is actually causing the result of your stomach growling. Um, that is the actual cause of, not eating causes your stomach to growl, so that's causation. One event causes the other. So it says this can be described in this example, the acceleration happens as a result of the net force being applied. You would not observe acceleration if net force wasn't applied, so it's a causal relationship. If I increase the net force, then acceleration is going to increase so that they're directly related to one another. But acceleration does not cause a net force. Just because something's accelerated doesn't mean a net force is being applied. So one doesn't cause the other. So when I push it, it causes acceleration, but acceleration doesn't cause me to push it. That makes sense. I don't like the example. I honestly don't think it's a great example. It is going to direct you to listen to this podcast where it talks about increasing temperatures in the ocean correlated with an increase in shark attacks and how, they can see that one is related to the other, but again, not directly sure if one causes the other. And in science, it's really difficult sometimes to determine causal relationships or causation simply because there's so many variables in the natural world. In order to directly determine if something's causing something else, you have to isolate the variables, you have to have them in a laboratory type setting where you can control everything except for the one variable that you're testing. And in that situation, you can more easily determine if there's actually causation. So here on slide 10, so I move forward a little bit, they talk about reflexes. If a doctor strikes a reflex point, like by your knee here with one of those little reflex hammers, it actually causes the legs to kick out of the patient. When examining the motion of an object, according to Newton's second law, it's also fairly easy to see cause and effect. The push or pull of a net force acting on an object is associated with the object having acceleration, which is the rate of change in velocity. That is causation. One actually causes the other. Um, so the relationship between net force and acceleration is described as correlation because each quantity changes the other quantity. However, because net force causes the acceleration to occur, we can also say there is causation. So just kind of giving you an understanding of the difference between correlation and causation, and actually that both can kind of occur simultaneously, and or you could have one or the other. So when we look at this graph, it's giving you an example. What can you conclude on the graph? So it says we have our increase in year, the number of cars, and then you're getting percent of children with asthma, right? So as we're seeing here, as we increase the number of cars, so too do the percent of kids with asthma. What can you conclude from the graph? Based on the graph, the number of cars increased between 1950 and 2000. Also, the percent of children with asthma increased over the same time. So I want you guys to think about that for a moment. Does that mean that asthma is caused by an increase in the number of cars on the road? Is the reason why we're seeing a higher prevalence of asthma today because of an increase in the number of cars on the road? Based on this graph, can we tell that that is a cause and effect? And actually, that is not cause and effect. We know it's correlated. There is a correlation between the number of cars and the percent of children with asthma, but it doesn't mean that one causes the other. Just because two things are happening at the same time doesn't mean one effect causes the other one. Does a higher percent of children developing asthma result in more cars being driven? That seems unlikely too. Obviously, the reverse isn't true. You're not going to cause, more kids having asthma doesn't cause more cars to be driven, and the number of cars being driven um, doesn't necessarily mean there's an increase in the prevalence of asthma. So, let's see here. I mean, obviously the opposite sounds kind of ridiculous. You wouldn't have a number of children with asthma causing cars to be driven. But it is potentially, that an increase in air pollution causes more asthma, but that would probably warrant increased investigation, right? Because you can't definitively say one causes the other here. Let's see. Many other variables can cause the increase in asthma. Experiments in which only one variable is adjusted and the other variables are kept constant is needed to establish whether statistical correlations are actually causations. So, yes, there's an increase in the number of cars being driven, and yes, there's an increase in the cases of asthma. They're correlated to each other. Does one cause the other? You can't determine that based on that one statistic. So I mean that's pretty much the nutshell of this lesson, ladies and gentlemen. It's a pretty um, easier lesson, like no math involved in this one. If you have questions, of course, let me know. Otherwise, we'll see you guys in the next one.